We're going to download a new data set that we haven't seen today. It's called PBC Full, in case you want to download it and follow along. And I'm going to get a script for it as well. Before we get started, we're going to hopefully finish up survival analysis today or at the latest Friday. And before we dive in, I wanted to say something about the exam. So the exam, let me pull up our syllabus real quick. Second exam had been scheduled for Monday, December 5th. And what I'm going to do with that exam, instead of having an in-class exam, is I will make it available to you on Friday, the previous Friday, and you'll have until end of day on December 5th to turn it in. So it'll essentially be a take-home exam. That does not mean I'm going to try to make it especially hard as a take-home exam. My goal with making it a take-home exam is to give you more time to write some R code and do an analysis. I don't intend to make the analysis harder, but I want, my experience is it's hard for students to complete an exam that includes download a data set and do some R stuff in an hour in the classroom. So this way you'll have plenty of time to do it. Right, so that's the plan with the second exam. If we go back to our survival analysis stuff, we're getting close to the end, and there's a couple of things more that I wanted to talk about. Okay, so at the tail end of the notes, beginning slide 36, there's a few technical issues that can come up when we're doing survival analysis modeling. One of which is called a time-dependent covariate. So a time-dependent covariate, first of all, the type of covariates that we've been seeing so far with our survival data are the type of thing that's measured once at the beginning of the study, like your gender or your age or your treatment group, things like that are constant throughout the course of the study. But in some situations, you might have a covariate that as you're observing your people in your clinical trial, maybe every 6 months, are you still alive? A covariate could be changing in value from visit to visit. Prior incidents of heart attack, for example. At the beginning of the study, maybe the answer is no for a person, but after a certain amount of time, maybe they had one. And so their covariate potentially changed with time. Everything we've been doing so far with Cox models assumes that there is a fixed, constant quantity for each of the covariates. So it can happen that one or more of your covariates are not like that. And so what can you do in that case? One example, this comes out of the Vittinghoff textbook, Regression Methods in Biostatistics. If you look at the section or the chapter on survival analysis, this example is in there. So there's a lung transplant study that's referenced with 124 patients, each of whom is a child with cystic fibrosis. The interest is in what is the effect of lung transplant on survival. So survival time for the children in this study are listed from the time at which they are placed on the listing for candidate of transplant. So we have survival times from time of listing, which means that whether or not they get a transplant is not known until potentially further into the study. So because lung transplant could be no at the beginning of the study for a child, but yes at the end of the study for a child, lung transplant is a time-dependent covariate. What would you do if that's the kind of thing you have? One thing you could do is just redefine lung transplant as yes or no after the fact. So once we have collected all of our data on an individual, we could code that person's lung transplantation variable as yes if they got a transplant at any point during the study. So doing that type of thing can cause problems, can bring problems. For example, if we were to say that every child who ended up getting a transplant gets a 1 for transplant, and everybody else who did not get a transplant gets a 0. A problem with that is that children who get a 1 for transplant are going to be systematically better off than those who didn't. Children who lived long enough to get a transplant had to have a long survival time on average because, as the authors note, there are long wait times for a transplant and there's high mortality for this population while you're waiting. So if we code people as 1 or 0 and forget about the time varying bit, then everybody who gets a 1 is potentially being kind of systematically preferentially treated. They're going to have higher or better prognosis on average. So I say that to say time varying covariates are something that you need to be aware of and think about. There are better ways of dealing with them than what I was describing a second ago, just coding them as yes or no, regardless of what time it happened. There are ways to incorporate into a Cox model some complexity that allows for time-varying covariates. So, for example, if we were to define, remember that the Cox model makes this assumption that the hazard, which is evaluated at a time t, and in terms of covariates x, can be factored into this baseline hazard that depends on t but not the covariates, and a linear model term that depends on the covariates but not t. So if I have a time-varying covariate or time-dependent covariate, my x, my covariates, depend on t. So if we're going to try to address this issue, we're going to have to break the core assumption of a Cox model. It can be done, especially if we make it a simple break. For example, we might say x of t, time-dependent x, transplant, is 0 before transplantation and 1 after. In which case, we could specify kind of a stratified Cox model. We could say there's one hazard before transplantation and there's a different hazard after transplantation. So this can be incorporated into Cox pH. I think I have this reference up on eCampus. If I don't, I'll put it up. But this is a PDF reference that shows some R code for how to do time-dependent covariates with survival stuff in R. I'm not going to do any examples with time-dependent covariates. But be aware of them, and if they are a reality in your particular application, I recommend you do a little bit more reading and learn how to use R to handle them. Cox model is assuming that the covariates, the effects of the covariates, do not depend on time. If the covariates themselves depend on time, you can do some tricks with the Cox model to accommodate it. Another kind of trick that we can do with Cox models has to do with when the proportional hazards assumption does not hold. We've talked a fair amount about assessing whether the Cox model holds. We've seen the log minus log of survival curves plots, and we've seen the Cox.zph function that gives us p-values for whether the proportional hazards assumption holds. So suppose that proportional hazards does not hold with respect to a particular variable, covariate. What are we supposed to do about it? One alternative would be to do something other than the Cox model, do a different type of model that doesn't require this proportional hazards assumption. Another option is to, again, kind of stratify, allowing for a separate baseline hazard function for, in the case of a categorical variable, for each of the levels of that categorical variable. So imagine that we're looking at survival time as measured or as modeled in terms of some covariates, x1 through xp, and suppose that one of these x's is categorical and that we have evidence of non-proportional hazards with respect to that covariate. Remember that we can assess the assumption of proportional hazards with respect to every covariate. The assumption is that the hazards are, or the effects of each covariate do not depend on time. So we can check that for x1, we can check it for x2, and ... xp. Suppose that x1 is categorical and we don't have proportional hazards, apparently. What we can do is allow for there to be a separate baseline hazard for the levels of x1. If we do that, then it's essentially like we're allowing the effect of x1 to vary, or to vary with time. If there's a separate baseline hazard for each level of x1, then the effect of x1, the log hazards, will be allowed to vary with time. So it is possible to specify a stratified Cox model that allows for handling of covariates for which we don't have proportional hazards. The PBC data that I just downloaded shows us an example to play with this, and I'll show you that in a second. So with the PBC data, let's go ahead and go there actually. PBC data, let's get the script open, pbc.r, and okay. I want to make, instead of pbc.csv, I think the file is named pbc data full. Yeah, pbc underscore data underscore full. So I'm going to fix this. And some of my scripts use the attach command, some of them don't. So the ones that I have attach in them are usually my older scripts because I don't prefer using attach anymore so much. It works, it can work, but what attach does, just FYI, is if you load in a data frame, in the data frame, like let's load this one in, So we have this data frame with separate columns for each variable, and each of the variables can be either categorical or numerical. That's the nice thing about a data frame. But if I wanted to, say, refer to the variable Rx, R doesn't know what Rx is unless I say the element or the column named Rx in the data object. Or if I were to say with the data object, the variable named Rx. So if you were to do attach data, I'm not going to do it, but if you did do it, then you could just call the column names directly. If you say attach, then when you type just Rx, it knows what you mean. The thing I don't like about using attach is that, for example, down here, I play with the Rx variable, and in particular, I recode it. I just rename the categories from DPCA to treatment. The reason I did that was because I wanted to match the ordering that was used in the textbook. Like the reference group was the control group, and then I wanted the treatment group to be the group that's compared to the control group. But because of the coding that they used for the different treatments, it went the other way around. The treatment group was treated like the reference group, and the control group was compared to it. So I'm trying to just recode to force it to have the parameterization I want. After doing attach, then this will work. I could say Rx. I could directly refer to Rx. But if I make these changes to Rx like this, then the original Rx in the data object are not being changed. The original object Rx column in DTA is not being touched when I make those highlighted changes. If I want them to populate in the original data object, then I have to specifically go back and make the changes there. The issue is that if you have attached, then no changes will be shown to these variables unless you explicitly make them to them. So I prefer, as a general rule, to work with like the with command and the $ command when working with data frames. So I'm going to comment out DTA here. We'll probably have to make a couple of changes below to accommodate that. All right, so I'm going to library in the survival package so we can do Cox models. And I'm going to set aside two variables, one for event time and one for event censoring indicator. So TM will be our time, EV will be event status, censoring indicator. And if we look at the data, status is coded as censored or dead. We've been used to seeing zeros and ones. 0 for censored, 1 for dead. So I'm going to make that into the familiar coding. I'm going to say, first off, TM is the survival time. And then EV, if you do s.numeric status, it's going to code these as, I think, 1s and 2s. 1 for the lower alphanumeric level censored, and 2 for the second. I don't want 1s and 2s. I would prefer 0s and 1s. That's what we're used to. So I'm going to say s.numeric and then subtract off 1, turning 1s and 2s into 0s and 1s. So now we have 0s and 1s for our censoring indicators. And then this, like I said, is just recoding the treatment groups. Table data $Rx. We have placebo and treatment. All right, the thing I wanted to illustrate here was non-proportional hazards with respect to one of our variables. So we have several variables, and what I'm going to do next is ask the cox.zph function to assess proportional hazards with respect to some of these covariates. I'm going to consider treatment and edema. This is what the textbook did with these data. We could include more covariates in there, but just for simplicity, let's look at these two covariates, treatment group and edema. Cox.zph will ask, does it appear that the Cox proportional hazards model holds with respect to each of these covariates? Okay, so we get out a table, and the main thing we're looking at is the p-values. Large p-value for treatment group indicates no problem with proportional hazards with respect to treatment group, but we have a very small p-value with respect to edema. Remember that Cox-ZPH also gives us a global p-value for overall, does it appear like proportional hazards holds? And because it appears like definitely not for edema, the global p-value is pretty small too. So if I wanted to fit a Cox proportional hazards model for comparison group, treatment group, and edema, I have a problem because of this. The interpretability of the model is suspect, questionable, because one of the key assumptions of the model does not appear to hold. The effect of edema does not appear to be constant in time. So what we can do is stratify the proportional hazards model by allowing there to be two different baseline hazard functions, one for edema equal 1 and another for edema equal 0. That allows for there to be a time-specific hazard for each of the levels of edema. To do that, I'll show you the code. There is a strata argument to Cox-PH and also to several modeling functions in R, like LM and GEE, GLS. So if we say Cox-PH, survival time tilde, Rx plus strata edema, to Cox-PH that means do a stratified Cox model, allow for edema level specific baseline hazard functions. And let me show you what comes out. If I do that, what comes out is this. This is the collection of estimates and standard errors. Notice that there is no term, there was no estimate returned for edema. If I didn't stratify, like let's remove the strata argument and call this fit 0. Without stratification, we have estimates for both of those covariates. So one implication of stratifying is that you do not get an estimate of an effect for the variable you stratify with respect to. That's because it's being kind of handled by that baseline hazard function, and we don't get any estimate of a baseline hazard function from a Cox model. So it's like out of our model now. That's not necessarily a problem if edema is only intended to be used as an adjustment variable. I want to adjust for edema like a covariate, but it's not my variable of primary interest. In this study, my primary interest is in asking, is there a treatment effect? So I primarily care about the Rx variable and a p-value for it. I can't estimate the edema effect. It's being incorporated by the model, but because I stratified, I don't have an estimate of its effect. So having non-proportional hazards is a bummer. There are things you can do to try to address it, like stratifying here. That does come with some drawbacks in that we cannot do estimation of effects on the variable we stratify on. It's also harder to do this stratification if the variable is numeric. Categorical, there's only a handful of categories, so there's a handful of baseline hazards that we would need to have in order to accommodate it. But if it's a numerical variable, what do? You can't have an infinite number of baseline hazards. So we would need additional methodology to deal with a numeric predictor for which there is non-proportional hazards. A final technical challenge with doing survival data is something that came up in a previous lecture. Somebody asked about it in class. What if what if we're, for example, following individuals for death from AIDS? So we have people who are HIV positive who have AIDS, and we're following them to see what is the survival time. So when somebody dies of AIDS, complications like some infection that their immune system couldn't handle, then it's clear, we would say that person lived up to the time of death. But what if somebody what if somebody died from a bacterial infection or something that happened because they were in the hospital? It didn't have to do with AIDS. It was just an exposure of some other kind. Or a heart attack due to something other than the AIDS or the treatment that they were under. So an example from the Wittinghoff textbook is this one, where we have a cohort of men followed for 5 years, and what the primary interest is in is whether or not somebody dies due to cardiovascular event. So let's record survival time, time until death due to a cardiovascular event. But what happens if they die from cancer or some other cause, like got hit by a bus or something? If cardiovascular event is the primary cause of death that's of interest, then the other causes of death are actually causing some difficulty for us. What do I say when somebody dies after 18 months due to some cancer, but not cardiovascular event? My study is recording survival times for people with congestive heart failure or something, but somebody died at a particular time not due to a cardiovascular event. There is a whole set of techniques and methods that are available for trying to tease out issues like this when there is a so-called competing risks issue. And I'm going to refer you to the book for details on that. For our purposes, I want you to be aware of issues like time-dependent covariates. Cox model is not by default set up to handle that. Non-proportional hazards. Cox model is not set up to handle that, but you can get around it by using the stratification trick, strata. And competing risks, I think for our purposes, I'd like you to just be aware of that issue. If you're looking at event time data, we should be defining clearly what types of events are we expecting. And are there possibilities of this competing risks issue? If so, then do some further reading and think about it, because it could cause problems for you. Ideally, there's not a competing risk problem, but often in real-world applications like clinical trials, there are. Okay. The last thing I wanted to show you in the context of survival data is an alternative to a Cox model. So Cox models are widely used. They are, I said before, semi-parametric. They're not fully parametric, which is kind of nice. You'd prefer to not have to make parametric assumptions if you don't have to. But there are parametric models. The thing about parametric versus non-parametric is that if the assumptions of a parametric model hold, then that model will generally outperform a non-parametric or semi-parametric model. If the assumptions hold, you'll do better with a parametric model. More power, for example, higher power. The challenge is that if the assumptions don't hold, then it may be incorrect. The results may not be right. They may be wrong p-values, wrong confidence intervals. But in some cases, you have good reason from prior data. For example, we know working at Boeing that event times or failure times for this type of component in the airplane wing follows really closely a Weibull distribution or something. If you have some reason to believe, well, we've watched these types of data for years and we know what they look like, so here's a parametric assumption that seems reasonable. If you have reasons to believe a parametric model, there are ways to do survival-based regression with a parametric assumption. So one type of model that's parametric for survival data is called accelerated failure time models. So what an accelerated failure time model looks like is regression. And instead of working with a log hazard, AFT models use log event time as the response, which is kind of nice because you don't have to work with hazard functions. You don't have to talk about hazard ratios and log hazard ratios. You just talk about log survival time. So an AFT model would give us log event time equals linear model plus some error. What an accelerated failure time model does is, suppose we're comparing two populations, treatment and control, say. What an AFT model says is that there is a constant C that's bigger than 0, such that the survival in the control group at time t is equal to the survival probability in the treatment group at time c times t. That's like the survival at time t in this group is an accelerated version of that in the second group. Survival probabilities generally go down with increasing time. So if we're saying that the survival at time t is equal to the survival at some positive constant times t in the other group, then S1 of t has survival probabilities that are decreasing in an accelerated way. That's where the AFT nomenclature comes from. That has some ties to real-world applications, you know, like humans and dogs. We think of humans or dogs as aging at an accelerated rate relative to humans. 1 human year is roughly, the rule of thumb is that 1 human year is worth 7, or the other way around. 1 dog year is like 7 human years, right? So if your dog is 7 years old, it's like they're 49 years old as far as humans go. So that's kind of like this accelerated failure time relationship. The survival probability, your health prognosis at time 7 for a human is comparable to the survival probability at time 7 times 7 for a dog. Okay. So the way, when we do an AFT model, what we have in terms of interpretation of coefficients, what we have is that the event time, so I have written out 2 event times here. T1 is, T1 and T2 both have the same values of covariates, of all the covariates except ZK. So we're going to try to isolate beta K. What is the interpretation of a beta coefficient in an accelerated failure time model? Beta coefficients are mean differences in response for a regression model, linear regression. They are log odds ratios for logistic regression. They're log hazard ratios for Cox models. In an AFT model, what is a beta coefficient? So what I've done is written out Z1 and Z1. That's the same value of Z1. Hold all the covariates but one of them constant, and increase or increment the one, we're going to consider ZK, increment it by 1. So what we have, if you work through this, is a particular constant, C1, times another constant that is a function of these error terms in an AFT model. The error terms in an AFT model look a little bit different than we're used to. There's both an epsilon, like mean zero residual. There's also this scale factor that is also estimable by the model. So at T1, according to the model, the mean survival time would be this, and at T2, this is all the covariates are the same, except ZK is now ZK plus 1. What we have is that this event time is equal to e to the beta k times that event time. The mean survival time at time, or at ZK plus 1, is equal to e to the beta k times the survival time at ZK. So e to the beta k is like an acceleration factor of these mean event times, corresponding to a 1 unit increase in ZK, every other variable held constant. So you interpret the beta k's as an acceleration factor. We're saying that we have this accelerated failure time model. S1 of t equals S2 of some constant times t. And what it works out to be is that that constant times t is e to the beta k. E to the beta k is the acceleration factor. So an AFT model says that the survival times for two comparison groups are the same, except that one of them has accelerated times. And the beta coefficients, or e to the beta coefficients, tell us what those acceleration factors are. That's a little bit hard to interpret as well. Just like a hazard ratio is a little bit hard to say exactly what that is. It would be a little difficult to explain to a layperson what an accelerated failure time coefficient means exactly. E to the beta coefficient is an acceleration factor on the survival probabilities. Just like a log odds ratio and a log hazard ratio and a log acceleration factor, they're just kind of proxies that we end up working with because the models end up being tenable. The bigger beta k is, the worse off you are. If I'm accelerating the failure time survival curve by a bigger and bigger positive amount, then your prognosis is worse and worse and worse. So just like in all the regression models we've seen, extreme beta k's, or big positive beta k's, correspond to, in this case at least, decreasing prognosis. The nice thing about AFT models is that they can accommodate a variety of probability models. AFT models are parametric, so you have to specify a distribution to use. In fact, you have to specify two. You have to specify the distribution of the event times and a distribution of the residual terms. That's just by nature of the model. And these are common choices. So Weibull is often used for survival times, exponential, gamma, log logistic, log normal. These are all distributions that can't be negative, but they can be any positive number, which makes sense for survival times. Can't have negative survival times. So I would recommend your first stop with survival data is a Cox model. I think that's the most natural place to begin. If you have many issues with fitting the Cox model, there's just no proportional hazards at all, it's very clear that that assumption is not good, then you might consider something like an alternative, an AFT model. But I think Cox models are a good starting point. I was going to show you a better way to make these log minus log plots, but I ran out of time to do it. Remember that we made these pictures and it was kind of hard to tell whether the curves were separated by a constant amount whenever the curves curved. And what we talked about doing instead of this type of plot was a plot of differences of the log minus logs survival times. The problem with doing that is that the event times are not going to generally be the same for each group, so it's not easy to take a difference. What we would need to do in order to do that, so we might have two survival curves, that one, and say that one. And in order to make a log minus log plot of differences, we would need to have differences for a bunch of different time points throughout here and the corresponding survival probabilities, which we can find from the Kaplan-Meier output. If you tell me time points that you want estimated probabilities for, like all those green tick marks, we could go into the output and figure out what is the estimated survival at each of those times, according to each of these survival curves. I just didn't have time to finish the code, but it can be done. So if we have time, I'll show you how to do that maybe Friday. But okay, are there any questions about that stuff or the homework? That's all I wanted to cover today. Okay, then I'll let you go, and I'll see you Wednesday, or see you Friday.